Good morning, class. This is Monday, and we have just wrapped up Chapter 2 finally by taking the test last Friday. Those test scores are available in Aries currently, and as soon as there's a few people who haven't taken the test yet, as soon as I have those tests taken and secured, I will be posting your individual tests back into your shared folders so you can hopefully open them up and see how you did, see where there's some room for improvement, and celebrate some success. Um, I am going to make a point recovery quiz available for Chapter 2. That has to happen this Thursday and Friday. It has to happen on Thursday and Friday. Those are the only 2 days. And if you do not make it up on that Thursday or Friday, those points will not be available to you. I'd like to point out also that when you're not in my class physically, your avenue to what's happening in class is either the live lecture or these recorded lectures. So please make sure that you watch these in their entirety daily. If you don't, there's a lot of things that you miss. And I know that we live really hurried worlds and we try to fly through things, but I just want you to understand I see some of the work you're submitting and the things you're doing, and it's very clear to me, um, based on your view logs, that you are not watching the lectures, and it's impacting your understanding as a result. Our section today is titled, How Can Algebra Tiles Help Me Multiply? And it's interesting that we bring this up now because on the last test there was a problem that you could have done completely with arithmetic and not had this error. But um, there's some misconceptions that pop up, and I understand why. We tend to overgeneralize things. Humans are pattern recognizing engines, right? We recognize patterns. Unfortunately, we do it badly sometimes, and we will extend our patterns into places where it's not true. It's good to notice things, it's good to observe patterns, but sometimes where we extend them is not correct. And this is a good example of that. One of the things that you probably notice is that if you have a product and you're raising it to a power, it is perfectly fine for you to raise each of the factors in that product to the power separately. So when I do this, right, I can verify that I'm correct. When I do this, I end up getting 4 times 9, which is 36. The other way I can do this problem is I could multiply the 2 times 3, get 6, and then when I square the 6, I also get 36. So you see, by writing this as without the parentheses, by writing it this way, right, it's completely valid because they both produce the same product of 36. But I want to observe what happens when we come over here and we apply what we think is this pattern to a situation where we have terms and not factors. So when I what I see happening is that people will think, oh, I can, and I should put a big old like, no, don't do this, right? Because I don't want you to think that this is what's happening. But and you'll see that the numbers don't work. But what I saw happening a couple times on our last test was some people would say, well, that's going to be 2 squared plus 3 squared, and it seems fairly reasonable, like fairly reasonable jump because we've observed that that works with factors. Why couldn't that work with terms? Well, if you look at it, this ends up becoming 2 squared is 4 plus 3 squared is the number 9. 4 and 9 together is 13, right? Over here, if I add these first, I get 5, and I know order of operations would, well, I would have to add these first, right? I add them, I get 5, and when I square that, I get 25, and I can clearly see that 25 is not the same thing as 13. So this means that if you have a series of terms, things with plus or minus raised to a power, you cannot you cannot um, raise each of the terms individually to a power and think that you're going to get the correct product. You can think about this though in terms of a rectangle. And I want to show you what I mean. So if I'm multiplying 2 plus 3 rather, 2 plus 3, and I'm squaring that, that's equivalent to me multiplying 2 plus 3 times another 2 plus 3. And I know what you're thinking, Mr. Roberts, those are both 5. 5 times 5 is 25. We're done. Why would we keep looking at this? Well, because I want you to understand that sometimes we do this with things that are not numbers. So for example, I could be doing this just as well with a plus b, right? And I could want to know what do I get when I multiply that. So please understand there's a bigger context, algebraic context here, but I want to look at it with numbers because we understand those and we can think about those. So one way to view this is to look at an area model. So I know that this is actually a perfect square, but I'm kind of sketching this as a rectangle. And I want to show you that just very generically, I'm going to say that the dimensions of this piece is 2 units long. Like this piece from here to here is 2 units long. And then I add some more to the length of this rectangle. This becomes 3 units long. So this is 3. And as I look at the height of it, this is, so the height now, so I just did this 2 plus 3 here. Now I'm looking at the height, I've got 2, and then 3 more. 2 plus 3 more. So I end up getting these 4 rectangular regions. And if I look at them, right, I can multiply the 2 times 2 and I do get 4. And over here I have the 3 times 3, which is the 9. And that's the incorrect answer I got before, right? Remember, I got the answer of 13 if I thought I could square the individual terms and get the correct, it would be a product where I'm squaring something, but I didn't get the right product. And that's because I was missing this 2 times 3, which is 6, and this 2 times 3, which is 6. So if I add all these pieces up, right, what do I have? I have 4 plus 9 more plus 6 plus 6 more. Well, this is 12 and this is 13, and when I add those together, I get 25. So I think the thing I want to communicate early on here is when you're asked to multiply some polynomials, realize that you can't just square or multiply polynomials by multiplying each of their individual terms. You have to think about this broader area model. So over the next couple days, we're going to be building towards that idea, and we'll be dealing with polynomials shortly. Today, we're going to look at some algebra tiles, and as you're looking at your CPM ebook, you will see that there are interactive algebra tile sets that you can use. Click, drag on the screen, and you can build answers to today's homework using those. I'm just going to be writing on top of the static ones here in our book. So it says the dimensions of some algebra tiles are shown at right. The algebra tiles will be named according to each of their areas. So if we're going to be naming these according to their area, let's get that squared away. If I have a tile whose dimensions are y units by y units, I would call this the y squared tile. So there's a y squared tile. If I have a tile whose dimensions are x by x, when I multiply x times x, I get x squared. And a tile whose dimensions are 1 by x, 1 times x would give me an area of x. So that's just a single x. And also we have some tiles that are 1 by 1, right? So if we see the small little ones that are 1 by 1, we call that the unit tile. The tiles have a positive side and a negative side. Throughout our textbook, the positive side will be shaded. It'll be shaded in. So if you look at these ones are shaded, that means that they have that value. So they contain the y squared. If they're open, they would be negative y squared. For each of the composite polygons formed by algebra tiles below, use algebra tiles to build. We're not going to be doing that, and it's fine with me if you do not. I actually just want you to watch and listen and take notes on this lecture today and not worry about an assignment. It says use algebra tiles to build the polygon. Flip the tile so that the positive sides of each tile is facing up. Sketch the polygon on your paper. Label each tile on your sketch with its area. Write a simplified expression that represents the total area of the polygon, and then write a simplified expression that represents the total outside perimeter. So if we were to look at this one first, right, the area is pretty straightforward. This is one of the tiles that's 1 by 1, so this is a unit tile. So the area of this area equals, I could say it's y squared plus x squared plus 1. Now, in terms of the outside perimeter, the many of the dimensions are going to be very straightforward. Some of the ones that are interesting are the ones that are like here. This is a fairly interesting one as well. So those two are interesting. Everything else is pretty predictable. So if I go around and start listing the perimeter, because this is a y squared tile, I know the dimensions of all of these sides are y units. This is an x squared tile, so these are all x's. This is an x. And then I've got a 1, a 1, and a 1. Now, this one that I've labeled here, I can see that the full tile is x units, but I've got 1 unit that's covering it up. So this tile, this dimension, it's kind of this greenish color, is x minus 1. And then this one, you can see the full length of it is a y tile. If I go all the way from top to bottom is a y tile. But part of that y tile is taken away. In fact, the part that's taken away is x units long. So this is a y minus x. So the perimeter is a little bit more interesting. So if I'm writing the perimeter down, I'm going to have to include, I'm just going to start here and go this way. So I've got 1, 2, 3 y's. So I'll say the perimeter is 3 y tiles plus I've got an x and x. So I've got 2 x's going around this way and this way. Then I've got 3 1's. I'll say plus 3. And then I've got this x minus 1 tile, or this x minus 1 dimension here. And I've also got this y minus x dimension here. So this can be simplified. I can see I've got some like terms. These are x's, this is an x, and this is a minus x. So it looks like there's only 2 x's in total. I have a 3 and I have a negative 1. Those can be combined. And I also have 3 y's and I've got a y over here, and those can be combined. So I would say the simplified version of the perimeter would be 4y plus 3x. Nope, because this x and this x are going to cancel each other out, so I just have plus 2x. And then a 3 and a negative 1 would be plus a 2. So this is my simplified perimeter, and above here I've got my simplified area. So in your notes, I would like for you to sketch this, and then I want you to find both the area as a simplified expression and then also the perimeter as a simplified expression. Pause the video, and once you have that, unpause it. We'll check your work. So what you should have written down in addition to this diagram is that the area is xy plus 3y plus an x. The perimeter is 2y plus 4x's plus 6. And the one thing that might be slightly difficult is this one dimension. If you look at it, the whole tile, this whole tile is y long, and we're taking away 1. So that's why we say that this is y minus that 1. And when I combine this negative 1 and this 1, that's 0. So my area and my perimeter. Okay, moving on. We're asked to take a collection of algebra tiles, and we're supposed to arrange the tiles into one large rectangle with the x squared tile in the lower left corner. It says remember to flip the algebra tiles. So once you've done that successfully, it says that we're supposed to sketch that. So I'd like for you to sketch that in your notebooks. Sketch what the rectangle looks like. So if you were using the e-tools from the book, it might look something like this. We are asked to move these around. I think all the tiles in this problem were positive. If I double click them or single click them, you can see they go from positive to negative. If I double click a tile, it'll allow me to change its orientation. And it said that I should start with building the x squared tile in the lower dimension. One thing that I want to make sure, I don't know if you've seen these in the 8th grade or not, but when I put algebra tiles together, I cannot place them along unlike dimensions. So this would be essentially me asserting that x is a little bit more than 3, and I don't know what x is. I can literally change the tile patterns. In fact, I can come up here on this slider and I can make the x's smaller or larger. So I don't know what x is. It literally is a variable. But I do know that this is always 1 unit long. So I can place the end, right, against the 1 like that, and that's completely valid. The other thing that I can do is I can bring an x tile. This is an x by 1, right? Its dimensions are 1 unit by x. I can bring it next to an x squared tile because this dimension is x. So part of the key is to arrange this so that you make a perfect rectangle, but you only have x and y parts lined up with each other. So once you have a solution that you're happy with, right, I would like for you to sketch that into your notebooks. And that's going to be one of the part of the images that you upload today for this assignment. So sketch that into your notebook. And then the other thing that we're asked to do is it says the area of the rectangle could be written as the sum of the area of all of its parts. Write the area of this rectangle as the sum of its parts. Simplify your expression for the sums of the rectangle parts. So I can see without even making the rectangle that I've got an x squared. I've got 1, 2, 3, 4, 5, 6 x's, and I have quite a few units. I would count those up. But then the other thing that I'm asked to do is it says the area of the rectangle can also be written as a length times width. So once I've made my rectangle by putting all these pieces in, you can see I can add some unit tiles here. I mean, this is not finished, but once I finish that off and I made a rectangle, I would be able to report what the length is and what the width is. Right? Or I could say this is the length and this is the width. But right now, right, this is from this corner where my cursor is to here, that's x units long. So if it's going to walk that, that's an x. And then this is a 1, and that's a 1. So right now, this would be x plus 1 in parentheses. And this would be, it's x plus 2 in parentheses. But I don't think that's it because I still have some more x's, and I've got to put all these pieces in to make a perfect rectangle. So once you have the rectangle and the dimensions, please make sure you neatly print that in your composition notebook and upload that image today. And finally today in class, I would like for you to do question 75. Again, this is our class work. I'm going to circle some of these that I want you to make sure you do neatly and include in your notebook. I'll end at this one. And I'll do one of them just as an example. So we're kind of all on the same page. So we're going to do E together. So for E, it says we've got 2x squareds, 10 x's, and 12 ones. Our instructions is that we are supposed to build a rectangle using all of the algebra tiles, sketch each rectangle, and write an equation that shows the area written as a product like x plus 3 times x plus 2 is equivalent to the area written as the sum, something like x squared plus 5x plus 6. So let's go ahead and look at E. So I've got this set up, and you do not need to use the algebra tiles. I'm just going to do this for visual purposes here, but I've got 2 x's and I've got 10 of these unit tiles. So my idea is to stack them up in such a way that I can put, I have to be able to put all these ones in here. And I think this will work out because if I look along the bottom here, I've got 1, 2, 3, 4, 5, 6. Oh, and I've got 2 this way. And I know that 6 times 2 is 12. So I have 12 of these units, so they should fill in this rectangle and complete it quite nicely. So if we were to talk about then the dimensions of this and writing the dimensions, writing the area is two ways. Let's take a look at that. So again, those were the tiles I was given, and I was able to organize them into this perfect rectangle. And I did place my x squared tiles down in the lower left hand corner. If I look at my dimensions along the top, right, this is x units long, this is 1, and this is 1. So I would call this x plus 2 tiles. That's the length from here down to here. And then going the other way, the other dimension, I can look at it along the bottom or the top. It's going to be the same value. Again, I see here's an x, here's another x, and I've got 1, 2, 3, 4, 5, 6. So this is going to be 2x plus 6 more. 2x plus 6. So my answer would be that the other thing that they wanted me to write this down was the two ways of writing the area. One is the product of its length times width. Well, the length I'll say is x plus 2, and I'll say that it's 2x plus 6 wide. And if I look at it the other way by just counting up the pieces add up to 2x squared, 2x squared plus 10x, and then plus 12. So that's what we're doing, and you're just going to do it for those four problems that I circled for 75. Whoops, not back to the notebook. For 75 C, D, G, and H. Just follow the instructions there. I don't have a big presentation or anything I'm looking at today. I just want you to submit your notes. It really shouldn't be more than 2 pages, but if you're efficient, you can do it in one. So make sure you post your notes from the problems that I've asked you to do and the things that we talked about today in class. And tomorrow we will read through the math notes in this section and talk about exactly what a polynomial is. But for now, I'll let you look at that on your own if you're curious.